And then once we get the notes completed, then we'll flip over to the activity. So I may go a little bit, in class, we'll probably do the activity halfway through, but for this class, we'll probably do it um, yeah, this class, I'll do all the notes first. In face-to-face, we'll probably do it halfway through. And then I'm babbling. And then I'm trying to change the screen that doesn't change. All right. Okay. I'll get myself together. So again, a lot of this is going to be vocabulary. So I said a lot of this. We have to understand the vocabulary when we roll through this. We have to understand that we talk about a parameter and a statistic. Okay. The parameter is a number that describes a characteristic of a population. So whether it be a mean, the average age of an NFL player, whether it be the proportion of people that have 401b, 401ks, it is talking about a population. Okay, the value of a parameter is usually not known, again, because it comes from a population. Very rarely do we know population data, because that would mean we'd have to collect the entire population to get a value from it. So most of the time we do not know parameters. Most of the time we were working with statistics, and that statistics comes from a sample. So we have to understand when we are talking about a population and when we're talking about a sample. Okay, now it's pretty easy to line up. A population is going to be a parameter. They both start with P. A sample comes from is based upon, as we get a statistic from a sample, both starting with S's. So if we get confused on whether we're doing a parameter or a statistic, it's whether it comes from a population or whether it comes from a sample. Okay. Now, again, understanding, and this is where I feel like I am dinking for the cheat points all the time when I go through a test. Okay, you may accidentally write down a mean mu when in reality it needed to be a X bar. Again, you have to note where it comes from, because if I have a mean that comes from a population, I have to use this guy. If I have a mean that comes from a sample, then I have to use this guy. Again, we have to pay attention to what we're doing. Okay, what data we are looking at. Okay, so again, in our first example. That's what we're doing here, is we're going to identify what we're looking at. Is it a sample or is it a population? So a carload lot of ball bearings has a mean diameter of 2.5003. This is within the specifications for the acceptance of the lot by the purchaser. By chance, the inspector chooses 100 bearings from the lot that have a mean of 2.5009 centimeters. Because this is outside the specified limits, the lot is mistakenly rejected. Okay, so within this problem, we have a parameter because it came from a population. We also have a statistic in this because it came from a sample. Okay, so my parameter, again, is denoted by a mean mu. So because this has, if it's a proportion, it's going to be P. Anyway, we have mean mu. So because this is the card load lot of bearings, that means this is going to be a population. And so that means that when we come over here and write this, is going to be mean mu is 2.5003 centimeters. However, if we come down here for the 2.509, the inspector chooses 100 bearings. So we just have a 100 bearings. I should have done maybe this at a different color. Let's undo that. Let's change this to a different color. Not that you could probably tell that. There's my 100 bearings. The 100 bearings is going to come from a sample statistic. So because it is a sample, now we're going to roll with X bar, and that means that X bar is going to be the 2.5009 centimeters. Okay, so again, that's what this activity is. It is just when you read it, when you come across something, am I writing down mean X bar, mean mu, or X bar? Am I writing down a P or a P hat? Okay, so we look at example B. A telemarketer firm in Los Angeles uses a device that dials residential telephone numbers in the city at random. Of the first 100 numbers dialed, 48% are unlisted. This is not surprising because 52% of all Los Angeles residents are unlisted. Okay. So since I'm working, I have my purple pen on first. We'll talk about the statistic first. Okay. The statistic is going to be, again, from a sample. The sample is going to be the first 100 individuals. So that means that we're going to have a p hat because it came from a sample, and that p hat is going to be the 48%. If I come over here and I am looking at the parameter, if I look at the other one, it says that 50%, 52% of all Los Angeles residents. So that means because it came from all, that means it's a parameter. We're talking about P. P is equal to 0.52. Okay. Again, holler out if you have questions. I tend to just ramble. I understand that I should probably try to get you guys to be engaged a little bit more and asking you questions, but the wait time and uncomfortability there, I tend to move on and just get the job done and do that. So we'll keep on moving forward here. All right. The next examples here. The average ACT score for for MHS students is 23.4 on the ACT exam. In October, the MHS averaged 23.1. Okay, so even though they both say averages, this is for MH students in general. So because this is MHS students in general, that is going to be a so something's going to be equal to 23.4. Is it going to be a mean mu? Or is it going to be an X bar? That's what we have to determine because we're talking about, we're measuring something. And in this case, this is the population of all MHS students. And so this one's going to get a mean. Okay. So that means this was a parameter. So that means that the 23.1, this guy here, he is a statistic. Ooh, horribly written. So that means a statistic is X bar. And so the X bar was 23.1. Your average speed while traveling on I-70 on your way to Topeka was 78 miles an hour. A police officer clocked you doing 83. Okay. Again, this is this is a mean mu again thing. I'll give it away because I'm colorizing it. But again, we have the parameter of mu. That was my average speed all the way over. So that's going to be 78 miles per hour. However, the officer clocked me at one individual spot. So that means that would be a statistic. Now, this is a little bit, I want to say squishy because X bar tends to mean the sample mean. And we aren't talking about a sample. The police officer didn't take a sample of my driving 5 times and then average those out. So again, this is more for understanding what's a statistic and what's a parameter. But there we go. Okay. Important terms. So when we look at this, what we're going to see is when we talk about the sampling variability, the observed value of a statistic depends upon the particular sample selected from the population. Typically, it varies from sample to sample. And hopefully in the movie activity, we'll see what happens to sampling variability when I talk about samples. So now instead of looking at a chart of the entire population, we're going to be looking at a chart of all the possible samples of sample size blank. And in saying those words, I realized that we had another activity to work on that involved sample size, and I forgot to get that in the module. Oh well, we'll survive. Okay. So the other word we're going to talk about is the sampling distribution. The distribution of values taken by a statistic in all possible samples of the same size from a population is going to describe the behavior of that random variable. So in order to do that, let's pop out here and look at this and see if I can make that make sense. Okay, so here we have a population. We have a population of, does it tell me what size? It does not tell me what size. Right now I'm going to take what's my sample size? There's my sample size, 5. Okay, so if we wanted to, we could change my sample size to 10, to 16, to 20, to 25, but we're gonna leave it at 5. When I animate this, so there is my first sample. So from that population, up here in the top, you can't see me pointing, okay? But up at the very top graph, that is my population. It's going to be a normal population. In the second graph, that's my sample of 5. And so what happens is I got those 5 individual values and I took an average of those 5 values, and that gave me the blue dot in the third bar. So that would be one of those, okay? So when we talk about a sampling distribution, we are talking about, and I don't know, I wish there was some way I could point, but it's that blue dot down there. It's going to be the number of blue dots. So what happens is if let's see if I animate 5 more. So there's my next sample. So there's those 5, there's the mean of that 5. I can animate 5 more. And there's the mean of that 5. And that's what we're going to do in the activity today. But what we're going to start looking at is we're going to look at what's called a sampling distribution. And that means that we're going to look at all the distribution of all samples of size 5 from a population. And we'll look at the characteristics and see what that does. Now, I'm going to leave this one alone for right now because no, I won't. Okay. So we're going to drop 5 more into there. Okay. And I'm going to drop 5 more in. I'm going to drop 5 more in. So these are all samples of size 5. And all I'm doing is in that sample of 5, I'm finding a mean of that 5. And we just continue to add 5 samples. We add 5 more samples and add 5 more samples. Okay. And we're hopefully seeing what is happening to my distribution here. Okay. So now what happens is I end up with a distribution of samples of size 5. Okay, and if I look at that distribution, I've added more and more to it. I'm up to, what am I up to now? 118, 123. So I've done this now 128 times. If we look again at my blue distribution graph, over to the left of it, it gives me the statistics of it. Okay, now what I want to look at, and remember we're talking about samples instead of actual things out of a population. We can see that my mean up above, the mean of my population, oops, I didn't mean to destroy that. Okay, there's no edit undo. The mean is now 16.29 because I touched it with my pen. Okay, if we look at the mean down below, and again I screwed that up. No good. I'm sure you wanted to hear me do that. All right, clear lower 3, and we're just going to drop 10,000 in there. There we go. We'll just do that. Okay, so this is going to be 10,000 repetitions. My mean of my population was 16.29. The mean of my samples is 16.25. So my mean stayed in roughly the same spot. However, when we go talk about the sampling variability, we can see the population. And again, I wish I had some way to point. I need to figure that out maybe. If we go back to the original population, it had a range that went from 3 all the way over to roughly 30. However, if I look at the range of my sampling distribution, we see that it only goes from, it looks like about, 10 over and up to 20. So we can see the sampling variability decreased tremendously because we're talking about samples of size 5, okay, versus individuals. Okay, so again, that's kind of where we're headed. I wanted to use that as a precursor because I didn't know that the important terms of sampling variability and sampling distribution, I don't think that quite didn't get explained well just in words and notes. So I wanted to talk about what that was. Okay, so the blue is our sampling distribution. The sampling variability is going to be the amount of variation that occurs from samples versus a population. And we'll go back to notability here, and we'll keep taking notes. All right, population distributions versus a sampling distribution. So again, that population distribution, It's all members of my population. Okay. When we talk about, so that's my population distribution. When we're talking about, okay, that statistic at a bunch of samples, when we talk about putting all those samples together, we have what's called a sampling distribution. So again, a population is going to be that from that parameter. It's for all members. When we talk about a sampling distribution, it is going to be from a statistic, and so therefore it's going to be from a bunch of samples. Okay. This next part, I actually struggle. I don't know. Maybe I should have taken this out now that I have control of what's here. Anyway, a statistic is used to estimate so a statistic is going to be used then to estimate a parameter. Okay, so if we jump back to this guy, even though we're talking about a bunch of samples, we had the center of my sample ended up being roughly the center of my population. So that means that I can kind of infer that the mean of my sample is going to be roughly the mean of my center. And that's what I have to determine in there. So what we want to do is we want to make sure that we take this sample in an unbiased way. So that statistic is used, it is going to be unbiased estimator of mean of a sampling distribution, and it's going to be equal to the true value of the parameter being estimated. The variability of a statistic is described by the spread of the sampling distribution. The spread is determined by primarily the size of the random sample. So let's flip over here and look at this real fast. So we just said that the variability is dependent upon size. Now I used samples of size 5, okay? We can see down here next to the 3, there's the sample of size 5. So now I wish I had some way to mark this. I could take a picture of it and mark up the picture, or we can just try to remember. So remember that when I used samples of size 5, my variability ran from, let's see if I count this over, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it's roughly 10. We'll say it's roughly between 10 and 20. Okay, but now I'm going to change my sample size. I'm going to double my sample size to size 5. This is from 5 to 10. And I'm going to drop those same 10,000 in there. And now what did we see? What happened to the variability of my samples? Okay, we can see now instead of the very left-hand side being at 10, now it's at 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it moved in a little bit. It's very narrow. And the deal is, okay, let's say we pulled a sample of ages of people in my classroom. If you guys were just sitting here, okay? Now, typically, if I took a sample size of 3, let's just do 2, okay? You and someone else, everybody's going to be 16, 17, or 18, okay? However, if you throw me in there and 47, my value of 47 is going to make a sample mean be an overestimate of the true mean, okay? But if it's just me and someone else, let's say it's me and so me at 47. So let's go back to something I can write on. So let's say I was and I wish I was 47. Okay, I'm 49 years old. Okay, and let's say the other person in the sample was 16, and we add those together. That's going to be 54. My God, where'd I get a 4 at? 17. Okay, it's not even going to be 17. It's going to be 15. Oh my God, really? Whew. Okay. So 15 carry the one there's 65. 65, half of 65 is going to be 32.5. So with only 2 people, that sample mean turned out to be 32.5. So that's why I would plot in that distribution. Okay. However, if I throw a third person in there, okay, 49, 16, and 17, and we found that average, okay, that's going to be what I can't even. It's going to be 22. It looks like. Here are the 2, 6, 7, 8. So it's going to be 82, and 82 divided by 3. And I don't have a calculator handy to do 82 divided by 3. Sorry, trying to reach my calculator. And this is where I really wish I could see your faces to know if you're all sleeping. Oh my gosh, I'm sorry. 27. So the mean of that one is going to be, I turned off my pen. So we can see even that when I got that huge, when I got my age in there, that had a dramatic impact on my sample mean. It turned out to be 32.5, which is a way over the true middle. However, if I had a third person in there, okay, and you still got me, the large age in there, that buffered it. It got it down to 27.5. So as my sample size increases, even though I get one of those large dramatic numbers in there, okay, it is going to help buffer that out. So as my sample size increases, my spread is going to decrease. Okay, that was what we needed to get after. That was the moral of the story that we needed to get out. Okay, so if I change this now to a sample size of 20, when I animate this and hit 10,000, we're going to expect then to my distribution to be even. I want to refresh that. I wanted to. There we go. Back to the original population. So now we're going to jump this up to 20. So what we should see when I animate this 10,000 times is it is going to be a really narrow sampling distribution. Okay. And that's what we're after. Okay. So that's a sample versus and again, the whole point there was, and I way over talked that. Okay. But as my sample size increases, my variability is going to decrease. Okay. Spread. The spread of a sampling distribution does not depend on size of population as long as, so this is one of the first rules we have to remember, okay, that n, my sample size, has to be less than 10% of my population. Okay, so this is for my independent rule. So n equals my sample size, and n is going to be equal to my population size. All right. Moving forward, use sample from less than 10%. Okay. Given a choice of statistics to estimate an unknown parameter, choose one with, we want no or low bias and minimum variability. So if we look at this one, again, your accuracy is going to be, this is very inaccurate. So therefore this one represents high bias. Okay, this one also has high variability because it's kind of all over the place. Okay, so if we look at this in the form of targets, okay, or I could choose something. This is good because this has low variability to it. However, because I did not come close to the center, this has high bias. Okay, now even though I got some here in the center on the next one, okay, we're spread out all the way around it. So this one actually has low bias because I didn't focus on one part of my target. But it has high variability because it's kind of all over the place. And that's my last example because, again, we are focused in on one area. This is going to have low variability. And because it is all on the center, this is going to be low bias. And I can't say that we're going to see a diagram like that ever on the AP exam and be able, have to talk about variability and bias, but it's just a visual description of what we're trying to do here. We want to have very little bias in my sample, and we want it to be large enough so that we have low variability. Okay. All right, so let's talk about this. Okay, this is my sampling distribution versus a sample mean. Okay, so back earlier when we were discussing, I remember as my sample size increases, my variability decreases. So here it is. This is coming from, if I have a normal distribution to start with, so my population distribution is normal. Okay, so that automatically means sampling distribution will automatically be normal. Okay. So again, and that's just one of the key things that we're going to be asked, is my sampling distribution normal? And we're going to have different ways to say, yes, it's going to be normal because my population was normal, okay? Because my sample size was large enough, okay? And that's what we get down into, okay? If we have, let's say we have a uniform distribution. I'm not sure if we go back to this, is uniform one of my options? There it is. There's uniform. So there's a uniform distribution. So there's a sample of 5. We'll animate it. There's a sample of 5 from that population. What's it doing? Where's my sample? Oh, my sample size is still on 20. So there's my 20 samples, and I popped a mean. Okay. We'll animate it one more time as I'll talk through that. Just to understand what it did there. It's doing a sample of 20. So it's randomly sampling 20 out of that uniform population and then dropping out a mean of that sample. So we're going to do 10,000 of those. And sure enough, look at that. We have a uniform distribution. Okay, not a unit. Even though my population was uniform, the sampling distribution, because it's a bunch of samples of all sizes of size 20, that came out normal looking. So this is the odd part about inference, and the fact that, all right, I had a population that was uniform to start with. However, I can do normal calculations on samples because the sampling distribution is going to be normal looking. Okay, and I think I misspoke again. Okay, I had a uniform distribution. So if I go back to my notes here, that's what we're talking about. I had a uniform distribution. But if I come over here and I take samples of size 30, I'm going to have a distribution that looks like this. If I have sample size 60, I'm going to have a distribution that looks like this. If I up that to 120, my distribution now looks like this. So we can see the larger my sample gets, the smaller the variability is. Okay. So again, this is going to be, and again, what happens is we're going to get to a critical value. Okay. So let's come back here and come out, let's do sample sizes of 5 again. Actually, let's do sample sizes of 2. Okay. And we're going to, let's just do 10,000 of that. Now, again, that appears to be somewhat normal. Okay. But what happens is I have to have a certain size. Let's bump that up to 5 now, and we're going to animate 10,000 of those, and that is much more normal looking. And we're going to jump that up to 10, and we're going to animate. I don't want to animate that. I just want 10,000 of them. Okay. So now as my sample size increases, again, that variability decreases. Okay. There's that fit normal. So if I go back, I clear the lower 3. Let's do sample size of 2 again, and we'll do 10,000 of those. And it's kind of normal, kind of normal. All right, let's go back to this. Okay, now here it is. Here's the part about that our activity today was supposed to be about this. Okay, and we'll still get to the activity because it's due for a grade. I've only been talking for 30 minutes. I'm sure to you guys it felt like 30 years. Okay, because actually to me it felt like 30 years too. Let's talk about a skewed distribution. What happens on a skewed distribution? And again, this is what's supposed to be the activity today, but I don't want the normal on there. We're going to go clear the lower 3. We're going to change this to uniform, and now we're going to change this to a skewed distribution. Okay, so here is a distribution that is clearly skewed to the right. Okay, and I want to see what happens to that sampling distribution. So we're going to leave my samples at size 2. And we're going to drop, so again, I'm going to animate one sample. So there's my sample size 2. There's where the mean came out. I'm going to do 5 of those, and I'm going to do 5 more, and 5 more, and 5 more. And I'm just going to keep on adding sizes of 5. And I'll click too fast, and it wasn't thinking here. I don't know. But we can see that my sampling distribution on size 2, my sampling distribution is still skewed to the right. Okay, so that means my sample size is not large enough. So let's move that up to 5. And I'm going to drop 5 of those in there, and 5 more, and 5 more, and 5 more. And I'm just going to jump to chase and do 10. Now that actually appears to be almost normal looking. But what we could do is clear this over through. All right, so let's we're gonna make this more drastically skewed to the right. There we go. Okay. All right, so if I add that actually made it more skewed, made more normal looking. Anyway, so the point is, even though my population is clearly, wow, oh my gosh, clearly over 3, I'm gonna have to reboot the page because I've completely jacked it up now. Okay, even though I have a skewed population, so since my population is skewed, I cannot do normal calculations with it, but if my sample size is large enough. Here we'll do 5. We'll go back to that sample 5. I do 10,000. My sampling distribution appears to be fairly normal. If I bump that up to size 10 and I do 10,000 of those, now it clearly is normal. Okay. And so if even if I go higher, I go up to 20 and I do 10,000 of those, again, my sampling distribution, even though it came from a skewed population, is going to be normal. So therefore, I can do normal calculations if my sample size is large enough. So we go out to here, okay? And again, we're looking for will be normal if. Now, here we got lucky. It says n is equal to 4, n is equal to 32, n is equal to 16, and that appears to be fairly normal. But we can't do it, okay? Normal if my sample size is greater than 30, okay? So in this particular case, this we can't say normal, okay? So this is not normal because my sample size is not large enough. This one's not normal. Even though it looks it, in reality it's not normal because my sample size isn't large enough. However, this one will be approximately normal because my sample size is greater than 30, okay? So as we increase the sample size, the sampling distributions become more symmetric and eventually appear to be almost normally distributed. And the variability is going to decrease. Okay. So that's the two things that we have to remember. As my sample size increases, it's going to become more and more normal. But as my sample size increases, my variability is going to decrease. So therefore, my standard deviation gets affected. And that's what we have to roll into when we talk about this. Okay, so I don't think in reality we're supposed to hit this today. I think I still want to hit it today. So properties of a sampling distribution of a one sample mean. So what we have here is this. It means this. The mean of my samples is going to be equal to the mean of my population. Okay. Now, if we go back out to, let's see if I can do this. Let's see, do this and have it make sense. Formula sheet. There it is. All right, so let's clean this up a little bit. Okay. So there's my descriptive statistics. We're not talking about there. We talked about probability. We just got out of that. Now what happens is we're working with sampling distributions. That's an eraser tool. Sampling distributions and inferential statistics. So that's what we're working with now, okay? So what's going to happen is we can come down here and we're looking at means, okay? So we have the mean, let's talk about what this statement means, okay? We just wrote this down. The mean of my samples is going to equal the mean of my population, okay? That's what this is telling me. The mean of my samples is going to be the mean of my population. The standard deviation of my samples is going to be equal to the population standard deviation divided by the square root of n. Okay, because we saw as we increased my sample size, my standard deviation decrease. The variability decreased, so that means my standard deviation has to decrease. So as n gets larger, this value then becomes smaller. Okay. Now, that is if I was knowing a population standard deviation. Most of the time, I don't know this. I know a sample standard deviation. So that means that we're going to have to pay attention to this formula and use it. But for right now, because we kind of gradually work our way into that, we are only going to focus on this one. So when I write this equation down, you have access to it. It's on your formula sheet. Going the wrong way again. Okay. So let's come back up in here. We got our notes key. We were here. The standard deviation. The standard deviation. That was a good noise too. The standard deviation of x bar is going to be the standard deviation of the population divided by the square root of n. Okay. Which changes. So again, I have to pay attention to is it a population standard deviation or is it going to be a sample standard deviation? Okay. All right. So we're going to take out the ITY and we're going to approximately normal can be assumed when one of three things happen. Okay. And we kind of talked about this on the other page. Okay. If my population is normal to begin with, the sampling distribution will be the normal. And here's the key for any size n. So I could go ahead and use that sample size of 2 if my population is normal to start with. Okay. It is going to be approximately normal if n is sufficiently large. And here's where we got to talk about this is, and again, this just became one of just in the statistical community. We just arrived, over time they arrived at this number. I can't say that there's any magic. There was any calculation that came down with, hey, it's going to be 30. Okay. But that's what we have to pay attention to. Okay. So if I am not told my population is normal, then my sample size has to be greater than 30. And then if I'm dealing with actual data, sometimes I can get by with my histogram is unimodal or not symmetric, but symmetric. Okay, 2 M's. Symmetric box plot. Okay, so again, it's one of those things when we start doing inferences, we're going to have, is it a normal check? And my normal check is going to be one of those 3 things. Okay, so because it turns out to be that because it's going to be something that's going to be normal, my sampling distribution is going to be normal. Now I can do those normal calculations. So now we can actually go back and we can do a z-score, except my z-score is going to be my sample mean minus the population mean divided by my new variability, but my standard deviation now becomes this. Okay. So that's what's different about what I'm doing. And if we write what all these things in here, my x bar is going to be my sample mean. My mean mu is going to be my All right, I'm not for sure what happened there. Obviously, I lost my connectivity or something. I don't know. What time is it going to be? I'm killing time. Here, I need to get back to sharing my screen. So share screen, start broadcast. Let's just finish up this note spot, and we'll move the activity. So here we were with, this is my population standard deviation. And n is going to be my sample size. Okay. So I think I'm going to kick, we're going to kick notes in the pants right now. I'm going to hit stop recording.